So hi to everyone. So today I'm going to introduce our assignment, which is a bandpass filter. So first of all, bandpass filter is an electronic device or a circuit that allows signal between two specific frequency to pass, but that discriminates against signal at other frequencies. Some bandpass filters require an external source of power and employ active components such as transistor and integrate circuit. These are known as active bandpass filters. Other bandpass filters use no external source of power and consist only of passive components such as capacitor and inductors. These are called passive bandpass filter. So for our assignment, we are doing the passive bandpass filter. And also in this assignment, we can take a look for the bandpass filter and provide its details with the support of field data, including the facts, the values, the simulation results, and the calculation.
Very good morning to Dr. Suraya. My name is Ganesh Sanapraman. My matrix number is B08211-0151. So now I'm going to explain about the derivation of the transfer function. So this is the bandpass series RLC circuit. So from this is the main formula. H omega equals to V O omega over VI omega. So VO is output voltage. VO is output voltage, VI is input voltage. So from the output voltage we go to derive. So output voltage omega equals to R over R plus 1 over J omega C plus J omega C. So S we can replace it to the J omega. So R over R plus 1 over CS. S is the J omega, we substitute, we replace to S. So plus LS. So now we need to save the denominator. So what I did, I multiply with the S over L. So when I multiply S over L, so it become RS over L divided by RS over L plus 1 over LC plus S square. So then we substitute again, we replace again the S to J omega. So HS equals to R J omega over L, R J omega over L plus 1 over LC plus J omega square. So H J omega equals to J omega over R over L divided by 1 over LC minus omega square plus J omega R over L. So after we derive it, we get it this. So now we need to magnitude. So we have to magnitude like this. So H omega magnitude equals to W R over L divided by square root 1 over LC minus omega square plus omega R over L square. So the R over L, I make it omega naught. So omega divided by omega naught divide by square root 1 over LC minus omega square plus square root omega divided by over omega square. So after I get this value, I change it to the J omega. So J omega equals to inverse tangent W omega R over L divided by 0 and minus inverse tangent 1 over LC minus omega square divided by 1 minus the inverse tangent omega R over L divided by 1. So 0, this one we automatically will be 90. So 90 minus or J omega equals to 90 minus inverse tangent 1 over LC, because we divided already, so it will become 1 over LC divided by 1, so it will become 1 over LC minus omega square minus inverse tangent omega R over L. So because we divide with 1, so that's why we get the 1 over LC minus omega square, and this also W omega R over L divided by 1, so we get the omega R over L. So the final answer then I derive it again. J omega equals to 90 minus inverse tangent omega r over L divided by 1 over LC minus omega square. So in this, omega equals to 0 and hj omega equals to 0. So omega 0 inverse tangent 90. So the if the is it 9, if here 90 must here the answer also must be 90. So what I did, so 90 minus 0 equals to 90, I got it. So then omega square equals to 1 over LC. So inverse tangent equals to 0. So I get 0. So 0, here also the answer, final answer also I need to get 0. So what I did, 90 minus 90, I get 0. Then omega equals to infinity, inverse tangent equals to negative 90. So 90 minus 180, I get negative 90. So this is the magnitude of h omega graph, bandpass filter graph. Then this is the phase of h omega, a bandpass filter graph. So this is about the derivation of the transfer function. Now I'm going to explain about the types of the transfer function. In the transfer function, I have 4 types of the transfer function. First is voltage gain, second is current gain, third is transfer impedance, fourth is transfer admittance. So first we see the voltage gain first. So voltage gain, the voltage transfer function of a two-terminal pair network is defined as the ratio of the output voltage. So that appears across the terminal pair to the input voltage applied as the terminal pair. So the formula of the voltage gain is output voltage divided by the input voltage. So we can say VO divided by VI. So second, we see the current gain. So current gain, if we consider current through the component to be the input signal and voltage across the component to be the output signal, both expressed in terms of then impedance Z as equals to voltage and current is the transfer function for that component. So the current gain formula is output voltage divided by the input current gain formula is output current divided by the input current. So then the third is transfer impedance. The transfer impedance of the network is defined as the ratio of the voltage applied to the input terminals to the current which flows at the output terminals. So when the the ratio of the voltage applied to the input terminals to the current which flow the output terminals when it will connect to the ground only. So the formula of the transfer impedance is output voltage divided by the input current. So the fourth one is the transfer admittance. The admittance transfer function at each node of a circuit is equal to the ratio of the suspendance obtained when the node is open to the suspendance obtained when the node is shorted. So a transfer function in which the output quantity is a current and the input quantity voltage. So the transfer admittance formula is output current divided by the input voltage. Now I'm going to explain about the calculation of the frequency. So the formula of the frequency is f naught equals to omega naught divided by 2 pi. So omega naught we don't know the value, but 2 pi we can enter in the calculator, we can get it. So omega naught we need to find, we have to use the formula. So omega naught, the formula for omega naught is omega naught equals to square root 1 over LC. So the LC, right, we need to take from our simulation circuit value. So this the simulation circuit value. From this we need to take the inductor values and capacitor value. So what I did, just substitute in the formula and calculate it. So omega naught square root 1 over 3 millientry times 313 nanofarad, I get omega naught answer is 31.7 kilo. So after that, I enter to the frequency formula. F naught equals to omega naught divided by 2 pi. So 31.7 k divided by 2 pi. So the final answer I get frequency is 5.5058 kilohertz. So that's it of the calculation of the frequency.
So hi to everyone, my name is Chang Chun Han and I am from Group 9, and today I'm going to discuss the assignment for our Advanced Electrical Circuit subject. First, we are going to take a look at the circuit diagram. So the topic for our assignment is bandpass filter. Therefore, this is how the circuit constructed. Based on the circuit, we can know that the value of the inductor is 3 millihenry, the value of the capacitor is 330 nanofarad, and also the value of the resistor is 15 ohms. Now we are going to find out how to calculate the zero and the pole for this circuit. First of all, to determine the zero and pole, we need to start with our transfer function. Based on the transfer function, we know that transfer function is equal to R over R plus L plus C. And since L is equal to JWL and C is equal to 1 over JWC, therefore we substitute the L and the C with the equation respectively. We will get R over R plus JWL plus 1 over JWC. Next, we multiply the equation with JW over L and we will get R multiplied with JWL over L divided by RJW over L plus JW squared plus 1 over LC. After that, we substitute the JW with S to get the RS divided by L, then divided by RS divided by L plus S squared plus 1 over LC. From here, we can know that the numerator will be 0 and the denominator will be the pole. We substitute the value of the RLC based on our circuit, and finally the value of the 0 is 0 and the value of the pole will be 2500 and negative 2500. Okay, so next, this is the oscilloscope investigation on multisim. From here, we have used different values of frequency, which is 1K to 10K Hz to get the value of the voltage of resistor. So based on here, this is the 1K and 2K, this is 3K and 4K, 5K and 6K, 7K and 8K, 9K and 10K. So let's take a look at our table. So we can use the value of the voltage of resistor that we observe to calculate the current by using the formula VR equal to R. And from here, we will get all the current for each frequency. So from here, we can know that the Imax is 130.667. By using the formula 0.707 multiplied with the Imax, we can know that it is a 92.382 milliampere. So from the graph, we draw take a look at the exactly 93 milliampere, and we draw a straight line across the graph that we have drawn. After that, we need to observe the frequency for the graph. So we can know that the frequency of the center is 5K and the frequency from the left hand side is 4.6K and the frequency from the right hand side is the 5.5K Hz. So that's it from me. Thank you.
Now I'm going to explain about the discussion of this assignment. So the bandpass filter are used to isolate or filter the specific frequency within the range of the frequencies. A single resistor in series with a non-polarized capacitor is accurately set the cutoff frequency or the C point in the RC passive filter, but is depending on which way around they are connected. Either is a low pass or high pass filter can be created. The bandpass filter is a combination of the qualities of low pass and the high pass filters. The circuit is function as like a bandpass filter when one set of RC components is connected in the series, another set of RC elements is connected in the parallel. because the circuit comprises two reactive components. We get a second order filter. So one is one capacitor is for low pass filter, while the other is for the another one is the high pass filter. So these are the formula we apply when we doing the calculation. So in this equation, we can examine the actual portion of the denominator, which is negative omega 2 plus 1 over LC. When we set the equation to 0, we get a omega naught equal to 1 over LC. So then the cutoff frequency is equal to FC equal to omega naught over 2 according to the formula, and the origin of the transfer function formula is V out over V in equals to R over R plus J omega 1 plus 1 over J omega C. So this can be computed by using V in equals to V out V in, V out over V in to obtain the origin of the transfer function. The real of transfer function formula equals to V out over V in equals to R over R plus J omega 1 plus 1 over J omega C. So this formula, how we based on this formula, we derive it and get the transfer function formula is equals to V out over V in equals to R over R plus J omega 1 plus 1 over J omega C. So these are the discussion about the band pass filters. So finally we come to the conclusion. So in conclusion, what we learned from this assignment is RLC series band pass circuit is the combination of the three electronic components. First is resistor, inductor and capacitor. So the RLC circuit, RLC filter is which normally we call as a second order circuit, because which means that the circuit parameter such as voltage and current can described by a differential equation, second order circuit. So then the impedance of the resistor is a real number, and the impedance of the inductor and capacitor are pure imaginary number. The total impedance of the circuit is the sum of these three impedance and is therefore a complex number. So this section show that band pass filter can be made from the same circuit by simply switching the components. So then what we learned during the simulation and the calculation, what we learned is, we understood the formula, how to apply the formula for the cutoff frequency and omega naught. We understood how to use it. So before that, before we find the cutoff frequency, we need to find the omega naught. So then only we can do the cutoff frequency, because the omega naught, the frequency formula is equals to omega naught over 2 pi. So we have to find the omega naught value first, then only we need to find the cutoff frequency. So the omega naught formula is square root 1 over LC. So then we learn how to derive the transfer function formula. So we understood how to derive with that. Then we learn how to calculate the zero and pole calculation based on our simulation circuit value, and then this whatever we do, the calculation is based on our simulation circuit value Okay, then we learn to use the multi-sim software to build the circuit and run the simulation to obtain the output of the graph, obtain the output, and then we vary the frequency for get the output. So and then we recorded the output voltage in our result file. So finally we understood about the RLC series band pass series circuit.